Is my screen visible to you?
Yes, sir.
Okay then, we'll start. Right. So one more time. It's done. So we were about benchmarking the OS. So we wanted to have some numbers which is indicative of some performance kind of stuff. So with respect to that, tri-dimensional measure was one of the benchmarking aspect. So volume, so cube root of M1, M2, M3. So M1 stands for the million instructions per second. Normally it quantifies the what is it? How fast a processor works, or the million instructions per second. Then the second one was with respect to the interrupts per second, and third one was with respect to number of IO operations. So basically these are the three aspects. So one is computation, another one is with respect to the interrupts, so external events that are entertained, which also includes the uh, IO operations. So if you multiply that, now how much things are going with respect to that, cube root of that is normally a measure of how much thing or actual computation or say busy your system is. So some kind of measure which is indicative of how good or how bad of your system can perform, can be quantified with respect to that. So tri-dimensional measure. Other than that, we also stated, because that is not available in the slides directly, so he's jumping directly to the other stuff. So there were somewhere around seven parameters. We studied unbounded pivot inversions, datagram throughput, and semaphore shuffling. So all this are in terms of real stone metric. So there are certain constants which are multiplied with respect to task preemption time, task switching time, so interrupt latency, semaphore shuffling. Uh, so whatever the all the seven stuffs after we see, just to name them if I have missed anything. So switching time, preemption time, interrupt latency time, then semaphore shuffling, unbounded pivot inversion, so then datagram throughput. So include all of them with respect to multiplying A1, A2 are the certain constants, and empirically determined whatever meant, what is meant by basically empirical and empirical values or empirical formula is with respect to the observations you derive some constants. So approximately with respect to market survey, so they are determined, and you get some metric with which you can say something is good or bad, or some number, or one identification number as such. Other than that, OS should be also should be able to process, or how much overhead with respect to interrupts is there, interrupt processing time or high interrupt processing overhead. So if T naught is considered the computation time or processing time of a particular task without any interrupts, and Tn is the time considered so with so many interrupts. Say in this example he's taking within 1 second there are 20,000 interrupts that are happening. So if there were no interrupts, the task T0 would have been completed within 1 second. So with interrupts, so what is the processing time? Tn minus T0 divided by T0 into 100. So what is the overhead? 1.6 seconds is the ultimately 60% of the additional time is required with interrupts. So that additional bonding or the overhead is computed. Burden on the system as such with respect to interrupts. Strictly speaking, we cannot say burden because interrupt might be happening for some reasonable reason as such. Two categories of benchmarks are important: deterministic benchmark and latency benchmark. Deterministic is yes, you can quantify something with respect to that. Measure of the determinism of operating system services. So how much deviation can be sustained? So there will be deviations, and the deviations are named as, say, first one is time jitter, response, and bin time. We'll look into the definition and description of the what is it parameters. Jitter. Can anybody state what is jitter? So task jitter we have stated already, maybe in the second or third chapter, I don't know. So jitter is deviation with respect to arrival and exit times. So most probably whenever you are doing your digital communications, you plot something like a eye diagram, right? So thickness of the eye, so that states or the at the both the edges somewhere there is a deviation with respect to that. Basically what you are doing is you are plotting your zeros and ones, whatever you have occurred, they have occurred with respect to some observation period or bit period TB ಮೇಲೆ overlap ಮಾಡ್ತಾ ಹೋಗ್ತೀರಿ. So then you observe that thickness of the opening, and then how do you define noise margins in the communication. Similar in the similar fashion, a task is expected to be on the clock edge, but it may be deviating before or after the so the actual arrival of the task may be deviating from the promised norms as such, and that is called as a jitter. Create a periodic timer and measure the deviation between desired and actual expirations. That is what is meant by jitter. So aspect tested measure of the response time on the operating system. So how much deviations that can happen with respect to the observance, that is tested. Time period 1 to 10 or 100 milliseconds. That is normally whenever you look into the operating system timings starting from the Windows, Unix. So it was 1 millisecond, 10 millisecond, 100 milliseconds. That's what we have observed. And if at all, okay, everybody has joined. So if at all okay, jitter itself is becoming large, then you may not promise the real-time operating system behavior for that particular OS as such. Then response. Execute a fixed processing load, measure execution time over a number of runs. So most often you determine if a thread can respond in a deterministic fashion. So it may be the ISR, it may be the task or whatever your that processing chunk has to process within a stipulated amount of time. So there can be worst case and best case or average cases, but the more it is predictable, so then it is more suited for the real-time applications or real-time operating system as such. So what is the parameters? Processing, add, copy. So weight stone, real stone, dry stone, and these are the spec benchmarks as we have stated. So with which you start measuring. So there's a actual or synthetic mixture of the instructions and across the programs or across the market survey. Okay. Bin time. Call a time of a day, clock, measure interval between calls. So how much interval is between the calls? So measures the maximum kernel blocking time. Say T1 and T2 whenever they are switching. So some kind of occurrence of events is measured with respect to the bin time. So what you are measuring is parameter which you are measuring is none. So most often jitter and response will formulate a benchmarks. Most often telephone calls and other things can be measured in terms of bin times, call a time of day, intervals between the calls. So that comes out to be a CBR and other things. So most often maybe in the next chapter whenever we are studying the real-time communications, so constant bitrate and variable bitrate communications. So we'll have some parameters over there, but with respect to RTOS, so the relevance of this is not that much. So time jitter. So there is a the bold lines are the things where they should occur, but there is a deviation between the arrival or exit of a particular task. So that deviation is normally measured in terms of, or it is called as a jitter, as per the definitions. Testing time. So how do you measure it? Create a timer, set it to expire at some period. When it expires, determine the actual expiration time. Deviation between the actual and desired expiration times with respect to that particular task is normally measured as a jitter measurement. Okay. Then testing time. So you can include a timer stamp. So he is using a system clock. As we have stated earlier, again, clock get time is a system call by itself, which again may be reading some hardware clock stamp as opposed to the Pentium 4, which is having a hardware time register. You can directly read from that. So otherwise, POSIX obtained system calls are making it happen. They give approximate timing again. They are not giving the exact timings. So use this stamp counter giving a high precision time of the day of the clock, so that you can measure. So ಯಾವಾಗ ಬರಬೇಕಾಗಿತ್ತು ಯಾವಾಗ ಬಂದಿದೆ actual. So expected and actuals. So that is what is meant by jitter. Now the second parameter was response measure. So measures the actual execution time. So for a 10 millisecond fixed block of processing, you know that without any interruption or without any hurdles as such, it can run take 10 milliseconds or one quantification. So you know the best performance as such. Whether or not the application response time is deterministic. So whenever it is running in the live sessions or runtime, so as a individual process, or whenever you say factorial of a number or a prime number, some functionality you are doing that. So as of only one application, you may predict a best performance for that matter. But it has some system calls in it, and if I require somebody's assistance, maybe in terms of IOs or maybe in terms of system calls, and how well I am served when I require the resources or I require any assistance. So it is different in the runtimes. So now you start determining the worst case behaviors. So best case and worst case, or the average cases, that can be if they are more deterministic in nature, you run for all the scenarios, and that can be a good measure of response measurements. So that just rough example is ATM machines. Say whenever they say 30 seconds is the time for card insertion, card validation, or any transactions you are doing with respect to the ATM machines. So it should not exceed 30 seconds. So some quantification or some fixed duration can be done, so that we design a system more realistically. Is generated with a loop consisting of one of the following operations. So how do you measure? You again have a profile. Normally code ಏನು ಹೇಳ್ತಾರೆ execution profiling ಅಂತ ಹೇಳ್ತಾರೆ. Execution profiling is if you have written a code, how many times a particular loop and stuffs are executed, and whenever you survey the execution profile of different programs across the market, then you have a good mixture of how many times arithmetic were executed or branches were executed and so on. You create something synthetic with respect to that, and so you can generate. Wheatstone is another set, similar to dry stone. Maybe Wheatstone is also incorporating the floating point operations, so that can be tested. A real stone is specifically for real stone, which includes your semaphore shuffling, task switching, preemption, datagram, all the 7 parameters. Fine. So it determines maximum kernel blocking time. Whenever kernels or the kernel blocking time is somebody is gaining a priority and blocking it. Repeatedly call time calculate the time required by each call. Indicates the time interrupts blocked. So whenever some task has acquired the priority of a kernel and it is running and it is blocking all the other stuffs. So for which amount, what is the task for the maximum amount of ಎಷ್ಟು block ಮಾಡಬಹುದು, that is what is your bin time. The time required by the response measure, the time required by each call consists of the time to perform the system call, any time spent in the mode change. So one is exactly to perform the system call. So there is some functionality you have to accomplish, but before to that you have to do the context switching. That is a spend time spent in a mode change. So most oftenly, strictly speaking, almost all application programs will be running in the application, the user mode. So whenever you want to accomplish something with respect to system or OS mode, then you have to go for the software interrupt or the SVC mode. So you go to the supervisory mode and then accomplish a particular task. So mode change sometimes, if there is a hardware support, may happen instantaneously. If there is no hardware support, may take some amount of time for that context switch. So as in case of, if I want to give an example of LPC2148 fast interrupt request, so you need not back up all the registers. So some of the registers are already physically available. They are logically mapped, physically available or physically duplicated, and hence you need not back up those registers, and the fast interrupt happens much instantaneously compared to the IRQ or slow interrupt in case of ARM LPC2148. Should be constant. So it is somewhere okay, kernel level benchmarking. So system call performance or the API or application program interface, whatever you are using, should have the consistent behavior with respect to its response time. That is what is meant by bin time. Maximum minimum time, it gives a good indication of the maximum time spent in the kernel. So again, worst case or best case, so in between there will be an average case. So whenever you know the worst case execution time with which all the scheduling were prompted, whenever you, if you can just recollect the second chapter, we were stating this sometime EI as worst case execution times. So more of a pessimistic approach what we followed whenever we were scheduling the tasks as such. So latency benchmarks, so synchronizations, sync measure the latency of a thread to thread or process to process synchronizations. So somebody is a producer, somebody is a consumer, and how do you sync between the production and the consumption? That is what is meant by syncing. So complete and you start using that resource. Measures the context switching time between the threads and processes. So basically, you are accomplishing a particular task in terms of threads. Multi-threading support or SMP was a support was debated in certain RTOS for that. Types of semaphore, POSIX named, unnamed semaphore, etc. So whenever there is a resource sharing, you have to flag it and then establish a sync, so that that particular resource is intact, or the integrity of the data or the resource is maintained as such. Message passing speaks about IPCs or inter-process communications, measures the latency of sending a data from thread. So if two processes or two tasks want to share something between them, so this is one of the benchmarks. So how fast you can put a mail and how fast he can read that particular message. Measures the possible throughput of data between processes and threads. So how fast a communication is between two threads or two tasks as such. Data buffer size, process to process or thread to thread communication. Then it will be simply to state that kill a process or stop. So those are normally indicated as signals. Measures the latency of real-time signals between two processes. When if I issue a kill signal or reboot signal to my OS as such, how fast it responds to that particular stuff, that is real-time signals. So kill is one kind of that signal where I want to kill a particular process or particular task. So how fast my signal is taken into account or you start processing it. So that latency you want to measure. Measures the latency of POSIX or the portable Unix real-time signals. So parameters you are measuring is none, but basically you are response time or latency with respect to signal to the response time. That's what is to be measured. So one signal on ಹಾಕಿಲ್ಲ. So synchronization again, latency of a system call. If you are making a particular system call and how fast the system call is, or the OS response to your system call, and response to maybe favorably or unfavorably. Round trip. So between the two tasks and there is a sharing. So then there may be the task preemption with respect to particular resource sharing. The task may have a different scenarios, maybe low priority or medium priority or high priority tasks that are to be debated or synchronization tests. So please observe that these slides are not in your textbooks. So textbook directly jumps for the determining kernel preemptibility and finishes the chapter. So only to because they are in the slides, I'm just continuing that. You have to, if you want to read that, you have to read in the slides itself. These benchmark tests include synchronization, message passing, RT signals. Okay, I think a single thread signals and then waits on a semaphore. So that waiting and signaling, I can explain better whenever we want to explore the some term work programs. Maybe you are not doing in this semester or never. But anyway, as a part of that course, it was designed earlier, and I will be sharing it. That. So test to use semaphores to signal between two threads. Threads are either a single or two different processes. So um, every task can create multiple threads, and then hence you can say the threads can be from the same task or different tasks as such. That's what is stated over there. Context switching time between the tests. So most often in the mid of the execution you find it out that's why t2 by t1, and you want to process complete the earlier one minus t1 context switching time. So if you want the exact diagram, you just go back to the task switching time diagram or the real stone metric. So then you will get a diagrams in your textbook as such. So assesses on operating system ability to deal with the priority inversions, latency benchmarks. Okay. So for medium priority tasks, a fixed duration processing loop is used. So it is for testing mechanism. So how do you test that particular benchmark? So you are using fixed duration processing loop. If a priority inversion occurs, the time between when a low priority task acquires a resource and when a high priority task receives it will be high. ಏನು ಹೇಳ್ತಿದ್ದೆ ನಾನು? The time between when a low priority task acquires a resource, so it has acquired it, and when a high priority task receives it will be high. So if there is no resource locking, definitely the lower priority task has to preempt and give it to the higher priority task. If OS synchronization mechanism prevents the priority inversion, that is you are locking the resource, or there are semaphores or some mechanisms of resource locking, then this time will be negligible. So that automatically the resource sharing protocols come up into picture, PIP or HLP and PCP, so that you give whoever has a resource will get a higher priority and let him complete with the stuff as such. The primary means by which operating system tries to meet task constraints is by task scheduling. So most often scheduling is a prominent aspect of RTOS. So additional operating systems such as Unix and Windows, soft real-time applications, most often the functionality is given a more prominence compared to the timing. So timing is there, but it gets back a second step as such. Whereas functionality and timing stand on the same platform in terms of RTOS or real-time operating systems. So embedded auto should be light and reconfigurable. That means custom tailored or custom tailoring should be allowed in the embedded system or the real-time operating system. Benchmarking can be carried out to compare autos performance. So that gives a fair choice. If you are well aware what is the functionality you are going to implement to a particular platform, and something similar to that with respect to that, you have quantified the benchmarking with respect to different RTOSs which are in the market, and you have also studied the portability issue of that particular RTOSs, then that gives a fair indication which RTOS should be used for your system message. So it's up to you to answer this quiz. Linux kernel operates at a higher priority than real-time tasks in Linux. True or false? Any answers? Yes, it is true because RT Linux kernels work on Linux, but Linux they should have at least same priority or higher priority compared to the Linux kernel. Then only you can meet the deadlines with respect to the terminology called as a real time. If you are developing a small embedded application, which of the following RTOSs would you use? So whenever you are making the decisions, so QNX, Linux, VRTX, Linux, whatever the terminology or particular flavor you are using, you have to give us a particular say justifications for your selections. In any project assessment, that plays a very important role. So whatever you are choosing, you are paying in terms of either money, human resource, or time. So what is really important with respect to that? So what are the trade-offs, and then you have to decide. So that's why we have gone for Q&As or links, that this should be much appropriate. Should an auto support virtual memory? Any answers for that? Yes, no? Okay. Basically, virtual memory is a bulkier affair. So that is a additional requirement with respect to the memory translations, maybe indexing or the translation look aside buffer, support for our virtual memory, maybe MMU or MPU, and hence it makes much bulkier, and predictability of memory access will be lost whenever you are normally going for a VM concept or virtual memory concept. And hence, as far as RTOS are concerned, they should be able to manage without virtual memory as such. If at all required, it should be as minimal as possible, so that the predictability is at a higher what is it and the higher priority compared to the accessibility. So virtual memory speaks about accessibility. I should be able to access 1 TB or infinite amount of memory, and that's how the virtual memory concept is built. Whereas real-time access speaks about this should happen within a stipulated amount of time. Okay, that you can use to benchmark RTOS. So what are the four important parameters that you can use to benchmark RTOS? So you can just state anything. So again, you can state the real time metrics by themselves. So we have 7 parameters. Other than that, you had a response time, latency, and bin time, jitter. So you can go on measuring them. So system calls and functional calls are indistinguishable. That means that they are running at the same priority. Otherwise, system calls will have a higher priorities, or they're running at a kernel space. Functional calls are running at a user space. Now, if you are making a statement, they're indistinguishable. So both are running at the same priority levels. That makes certain real-time functions to miss their deadlines. So, and which is not good for a RTOS or the real-time systems for that. So, can multi-threading result in a faster response time in a uniprocessor computer? We cannot comment for the questions like this. It depends upon the applications. As concurrency is good, say, but how much concurrency is really achievable is a question mark with respect to particular applications, and hence it's a debatable issue. So if there is a support and there is a possibility, yes, definitely it can be faster. So whenever you create multiple threads as such, explain an experiment to determine context switch time. So we have that create a context and then make it to switch for the make a next task ready. So then so task one is running, task two is having a higher priority, create a task with a higher priority, run it. So what is the time it takes from switching from T1 to T? So it has recognize that there is a arrival of a new task, and then actually it gives out to the new task because it recognizes it is the higher priority. After on the scenario create ಮಾಡ್ತಾ kernel blocking time. So make a system call and uh, see to it how much time it waits till the system call is served. So before we go to next chapter or real-time communications, I just want to finish off whatever is there traces with respect to the current chapter. So what we are left out with is inter-processing overhead. We have covered it already. So T naught is the processing time of that particular task without interrupt. T20,000 is within 1 second. There are 20,000 interrupts, and it is taking somewhere say 1.6 and 1 so 60% of the time additional time it is taking. So there is a 1.6 of the 60% of overhead with respect to that. So then there was a tri-dimensional measure. So you require some single numbers to indicate something, or I want to have a decisions or the orientation or tinge towards a particular aspect. So we had a number MIPS1, MIPS2, so instructions per second or the interrupts per second or the number of IO operations and cube root of that. will give you some single number, and then you can decide upon something good or bad. So kernel preemptibility is another aspect which has to be tested, and here trang is one aspect which normally is a program which where he says that it generates a triplets denoting three vertices of a triangle, and there is certain kind of processing that is targeted. So there are real-time tasks which are sharing the same memory, and they are generated, and whenever they are preempted, the behavior of those tasks with respect to the priorities assigned to them will be analyzed by the analyzer, and which speaks about the system kernel is preemptible, non-preemptible, and what is the preemptibility of a system by itself with respect to the priority of real-time task can be tested. So setup of a triangle, again one paragraph with respect to the generation of a task or the three vertices, some functionality associated with respect to that. So how best you can serve a system call with the priorities that will be fed through the analyzer, because you are generating vertices that are being fed to analyzer, that are being fed to memory, uh, and timer is fed to all the stuffs. So analyzer takes the timer as well as other aspects, and starts what is the preemptibility with respect to that particular system as such can be commented. So highly preemptible, non-preemptible, that can be commented, right? So that's basically playing around with respect to priority numbers as such. So that finishes your first chapter. But what we have left out as a case of okay, lab mode. So how exactly the kernel coding or real-time coding is to be done, or has to be explored as such. So can anybody explain what you are doing in the LPC2148 or the ARM lab as such? We are just deviating something from that, so that you are using kernel. ನಿಮ್ಮ ಎಲ್ ಪಿ ಸಿ ನಾರ್ಮಲ್ LPC2148 ಏನು ಮಾಡ್ತಿದ್ರಿ ನೋಡ್ತಿದ್ಯಾ? ಸೊ ಇಫ್ ಎನಿಬಡಿ ಕ್ಯಾನ್ ರೆಸ್ಪಾಂಡ್ ಬ್ಯಾಕ್. Yes. Okay, then. So this is simulator as such, but if you want to implement it, I can implement it with respect to the processor of choice. So NXP founded LPC2124, if you can state this. Um, whenever you choose a device, instead of firstly you wanted to select LPC2148 because you want to implement that particular system onto a particular platform. So all of them were containing the ARM 7TDMIS or the 7TDMI architecture. So we were having LPC2148 board, and all the peripherals associated with which will be made available for. So that is a device or target with for which we are designing a system. What is the difference we are attempting in this particular aspect? Or whenever I say project, new project, and choose a particular device, then so normally the OS was not taken into account whenever you are doing your previous experiments. So now I say that we will be having a RTX kernel, so that I'm calling RTX kernel for running a RTOS, or my applications will have to be in real time or predictable manner. So I will take assistance of the RTOS, so that the different tasks which are normally the daemon processes. Daemon processes means they are running for their lifetime. ನೀವು ಒಂದೇ ಅಪ್ಲಿಕೇಶನ್ ಡಿಸೈನ್ ಮಾಡ್ತಿದ್ರೆ ಮೇ ಬಿ ಎಲ್ ಇ ಡಿ ಬ್ಲಿಂಕಿಂಗ್ ಆರ್ ಕೀಬೋರ್ಡ್ ರೀಡಿಂಗ್. ಸೊ ಇಫ್ ಐ ಆಸ್ಕ್ ಯು ಟು ಮಿಕ್ಸ್ ದೋಸ್ ಟು, because keyboard reading is also a continuous process, you'd never know when someone will press a key. So there is a row scanning, column scanning that has to be continuously monitored by a particular program. So and hence it is a for or while one loop or infinite loop. So LED blinking also should be in infinite loop. Maybe there is a sensor, then it should also be scanned for every 30 milliseconds or some time duration of periodically. So and hence that also should be in infinite loop. Now how do you maintain so many infinite loops? So you require some scheduler, so which will switch between these different tasks, or there is some aspect of OS started peeping in, because every process by itself was a daemon process or never dying or while one loops. and hence you require one more person who is capable enough to switch between those three aspects as such. So that is what is meant by OS or the scheduler, to be very simple as such. So RTX kernel provides you such a kind of scheduler. So ಅದನ್ನು ತೋಳ್ತಾ ಇದ್ರಿ. So this thumb mode, thumb 2 mode, arm mode. So that speaks about what are the instruction set size or footprint you want to generate. So you are having a lesser memory, you may go for a thumb mode. You want to have a thumb 2 or thumb, say arm thumb mode. ನಿಮಗೆ ಯಾವ mode ಬೇಕಂದ್ರೆ, because ARM is a versatile processor which has a different instruction set architecture for the same processor. ಆರ್ ಬಂದರೆ 32 ಬಿಟ್ ಇನ್ಸ್ಟ್ರಕ್ಷನ್ ಜನರೇಟ್ ಆಗ್ತದೆ, ಥಂಬ್ ಅಂದರೆ 16 ಬಿಟ್ ಇನ್ಸ್ಟ್ರಕ್ಷನ್ ಜನರೇಟ್ ಆಗ್ತದೆ, ಥಂಬ್ 2 ಅಂದರೆ ಅಗೇನ್ ಮಿಕ್ಸ್ಚರ್ ಆಫ್ 16 and 32. And if I say your ARM also has a J term inside it, so there is a Jazile core, then it will also generate 8-bit instructions. So what you want to do, that is cleared over here. And cross module optimization is between the modules. So if there any optimization is possible, then you can just click onto the cross module optimizations. Normally I prefer to ask you to click on micro library because some of the functionalities are not implemented by the ARM vendor by himself. So there is a key compiler or third parties, they have designed their own instruction sets. Maybe we are using RTX kernel or some header files designed by them. So the libraries for them, it is as good as stating that to give an example, so maybe there is a no division instructions in the ARM instruction set. But if one of the code is using a division instructions, it raises an exception, then it goes some micro library or some kind of a microcode, and then routine see it will run that particular show. Then you want to include that micro library so that the additional routines are written over there, and hence there is a requirement for inclusion of micro library. Whenever you have chosen a particular device, so automatically the internal ROM and RAM addresses will be filled. So next approach is, if you want to implement this particular stuff onto hardware, then you have to create a hex file. Otherwise debug information and hence only simulation is possible. Fine. So listing and other stuffs, that is what are the files you are including and other stuff. It is as good as, so what you are listing, your memory map, call graphs or symbols, so global variable, local variables, all the lists will be prepared. Finally we'll go to the linker, so where you are clicking this terminology because your key compiler is capable enough to speak to your target board and fill these bases. So where is your ROM, where is your RAM? If you want to have it yourself, then untick, you know exactly what you are designing and you own the responsibilities, then fill the addresses appropriately. Fine. So after this, once you have completed, just to summarize, ನೀವೇನು ಮಾಡಿದ್ರಿ ಅಂತ ಹೇಳಿದ್ರೆ, so you choose a device. So maybe LPC2148, that is a better choice because that's the board we are having. He has chosen a 2124 for example program, whatever we are taking into account. Then linker, I'm clicking onto the stuff. Target, you are choosing RT Linux. If you want to have both the ticks, just tick them. Fine. So after this, what you were doing was, there was a startup code. So what is the job of startup code? So anyone, please. So we had some 7 exceptions or the 7 modes of operations and what should be done whenever, what is the exact address where it has to jump. So LDR, PC, reset address or reset address is, this is the address and what you have to do over there. So some code whenever you want to jump to that particular location. So you want to set your memory bases, you want to set the configure your clocks. So all whatever you want to do whenever system is reset will be done by reset handler. Whenever fast interrupt has handled, so you have to write some ISR routine or the interrupt service routine. ಅದನ್ನ ಬರಿತಾ ಹೋಗ್ತಿದ್ರಿ. Now I want to give a control to the RTOS. So SWI handler was mapping to some location, we have commented it because it's a part of RTL or real-time Linux now. So go to your startup.s code. So maybe in the 258th line or just type in or search for this SWI handler, branch SWI handler, this location. comment that SW handler, because we will be importing it from the other file. Which file? So we will be importing from the RT Linux, and hence import SWI handler. So your software interrupt handler is now done by the RTX Linux. So there onwards your OS takes over. So otherwise, so startup nalli you are configuring the things, then you will be jumping to the main program. ಇಲ್ಲಿ ನಿಮ್ಮ main ಇದೆ. In this you are initiating the OS system init OS. So we'll come back to this. What is this? So you are calling a OS, then you are creating a task, and you are assigning the definitions for the tasks as such. Fine. That's what you are doing. So much before to that, and there's one more file called as a configuration file. So this you are not able to see in the earlier things, or the ಮೊದಲನೇ programs or application programs, whatever you are doing in there. So at the maximum you are seeing only startup file. Now there is one more additional file called as a RTX configuration file. So this is your file. So there are two methods to fill this particular file. Most of the programmers prefer to fill it by the textual method. ನಿಮಗೆ ಇದು ಫಾರ್ಮ್ ಇರ್ತದೆ, and there are guidelines what are the values that should be filled into this particular stuff as such, or you can directly go with the configuration wizard. So task configurations. So number of concurrent tasks, running tasks. So RTOSs are to be more predictable. Normally the number of tasks, as you stated or studied across your commercial RTOSs, so they range from 5 to 10 tasks for that matter. So restrict the number of tasks that are running. So lesser, more predictable, more unpredictable. So limit it the task. So you want to restrict the number of tasks to 6. Number of tasks with the provided user provided stacks. So is there any private stack you want to assign, so that some manipulation can be done at a task level? Otherwise, a normal stack size is 200 bytes. So this is again you can manipulate this. So but normal stack size is 200 bytes, where maybe some data structure in some task requires a higher number of bytes, just to manipulate there. So additional 50 bytes or whatever you want to have it. So there is a private stack that is also made available, or can be made available. So then tick time configuration. So hardware timer, one timer is there. So again you have to go back to the check, say with respect to particular device. So now it is 2124. If you are 2148, the timers may be different. So 1 or 2, that is device over there. So it is showing 15 megahertz at 60 megahertz. You check your LPC 2148 whether it's at 12 megahertz or 15 megahertz, then map accordingly. So 1 millisecond or 10 milliseconds is your OS ticks or timer tick, or the with which actually your RTX kernel is running. So that can be manipulated. So system configurations. Now you want to choose a particular. ಅಯ್ಯೋ ಹೋಯ್ತನ್ರಿ, ಮತ್ತು ಆ ಹುಡುಗರು ಏನು ಕಮೆಂಟ್ ಮಾಡಿ ಒಂದು ಮಿಸ್